Okay, so hi, my name is Kenneth Chung, mechanical engineer under Dr. Caritas, and again, my project is Render. It is a low-cost actuated pin array. So to get it started, shape-changing displays are kind of a new approach to the ways humans can physically interact with computers and visualize 3D data. And many of the current designs, they operate with the same principle. It's just an array of linear actuators that together they form complex surfaces by raising and lowering pins to different heights. So I have two examples to demonstrate that. So I have MIT's Inform. You can see the individual pins raising to different heights all together because they are connected to their own motor by those red linkages. And then I have Elevate here, which is a little bit unique because the entire array is actuated by a moving set of actuators. But this technology has seen very little expansion beyond the research sector due to its high complexity and cost, mainly due to having a single motor per pin. And in addition, they're typically unable to withstand high loads without mechanical failure or component damage. So what my project seeks to do is to design and evaluate a pin array design that is both low cost, scalable, and can withstand high loads. It is intended to be used for applications such as VR integration and human robot locomotion tests. With this design, I also will explore how different actuation styles can be implemented. But this requirements can be broken down into certain specific criteria, and these criteria are so actuation. I got to make sure that the pins can be accurately actuated, and it's got to be reliable and fast. It's got to have mechanical strength. So we're going to be loading it with a human, so it's got to withstand at least 120 pounds. It's got to be compact, so I'm limiting myself to around 10 by 10 centimeters. It's got to be low cost, so roughly $10 per pin is like an estimate. And when we're thinking about an actuator, although this could be a project on its own, the actuator has got to be lightweight so that it could be fast and accurate. And this is a project that I started in winter quarter of this year, and I plan to complete it by the end of this quarter. So because parts actually are currently in shipping for most of the prototype, what I'll be showing you is the detailed model of the pin array as well as a preliminary prototype that I made just to test tolerances and make this additional adjustments. So this right here is the individual pin assembly, and it contains the components of the top surface block there. You can see it's made of 6 laser cut plywood panels. We have a rack, and it's just this rectangular bar labeled number 2, and it has a bunch of teeth in it, and that will be engaging with a pawl. And that pawl kind of operates like a seesaw and will be able to rotate out of the way and allow that rack to move up and down freely. And that pawl is able to rotate by a Bowden cable system. So it's essentially a fancy name for a bike cable, and it'll be able to pull down on the end of the pawl and move it out. And it's able to do so at the very end of the rack. And all these components they are planned to be glued together unless otherwise specified, just to reduce cost and weight. So when thinking about cost and simulations analysis, a 100 pin estimate will be used, and this is what it might look like. However, for practicality, only 4 pins will be used for prototyping. So the figures that I will show now is just to demonstrate what it might look like in motion. So this is just the lowest and the highest position of the pins. And this is just a zoomed in version of the linear actuator. You can see it's driven by a singular motor. This is a size comparison to a human dummy, so it reaches around your waist. And this is the pawl mechanism with a spring modeled in. So additional features on this assembly is that it has an electromagnet. It's that circular, that cylindrical puck at the end of that linear actuator. That enables you to pull the pin down. And unfortunately, this gantry will not be actuated. It won't move automatically because it's a small size and it's kind of irrelevant for tests. Although when you scale it up to 100 pins, it might work in a similar fashion to a 3D printer, or you might even scrap it entirely and add in like a swarm of mobile robots. So when I was doing that prototype to evaluate tolerances, I made all the parts to be manufactured entirely by laser cut. So this is what it would look like. And these are the prototypes that I have made. So starting on the very left, this is a frame that I made just to test the top surface blocks interacting with each other. And the single rack prototype is just the final design of that rack and pawl mechanism. You can see also that locking mechanism, what that spring looks like and how it engages with that rack. And on the very, very right, it's just a video demonstration of me manually pulling down on the end of the cable to move that pin up and down. But that process will be automated by a electromagnet. So to ensure that I cover all the requirements that I set out in the criteria, I performed some static simulations and calculations beforehand. So first, it's a static simulation. So I set the materials acrylic, put a 120-pound load on top of the very top, and it estimates around a 2.73 factor of safety, and it fails at that pawl. So what that means is that I can load 2.73 times the 120-pound load on top of it without it failing. And it's good that it fails at the pawl because that means it fails on a component that is really small and it's easy to replace versus the rack, which might collide if it bends. Frictional losses to the bolting cable, this is very important because we need to estimate how much force I need to put into the cable to pull back that pawl. So this is an experiment that was run by the paper titled here. And using their equations and findings, this is why when you looked at that cable I was pointing out, it has a singular loop. It makes it a lot easier to calculate that. So it estimates around 22% loss. So you need to put in 22% more force than you might expect. And because I'm pulling down at the end using a magnet, I need to estimate that as well. So using a 20 centimeter electromagnet, I estimate something as small as an M3 nut, which is the size of half your pinky finger. It's comes around 0.7% of the original rated pull. But because that's really, really small, I need to consider for the future of custom machining something out of iron that maximizes the amount of area to get something around 44% of the original rated pull. And the original pull is just placing a puck, an iron-like cylinder that maximizes the radius of the electromagnet on top. And that's just a data sheets. It's reported in data sheets. So for cost and making sure if it's low cost or not, I use the two examples that I introduced in the introduction. So here is MIT's Inform. You get around $45 per pin. I estimate this by taking all the materials of the pins and the motors and averaging it out across the entire assembly. Theirs is really high because they use high quality motors. Elevate is around $11.5. Theirs is really cheap because there's not a motor for pin. And mine comes around to be $9 per pin. And because of the independent locking feature of the pins, that allows hello, okay. This allows me to explore a unique actuation path that allows me to expand it to a mobile robot swarm. This inspiration comes from how open world games renders their world. So a common example would be Minecraft. So the following here is just a MATLAB simulation that I come up with. You may look at the final frame if it's a little bit too busy. So you can see how the robots, they are modeled in the blue and purple dots. They are going through the entire structure, trying to render that surface that I desired, following that red dot, and that red dot is supposed to represent a human. So what the simulation kind of represents is that it is capable of having a human standing on top of it while the actuators are doing their job. And it also streamlines the process of trying to figure out the weights and how they do their whole decision making, and just quickly make up this pattern. And yeah, I do have a lot of future plans. So in brief, I just have to receive the parts to construct everything and verify those numbers that I said before. And those are the parts that I have as of now. So, and these are my references. And yeah, that's about it. Thank you. And I would like to also give special thanks not just to my faculty mentor, but also a PhD candidate in my lab who's been guiding me throughout the entire process.
Thank you, Kenneth, for this great research presentation. We really appreciate